right, I'm getting a signal from Danny, so it looks like we're good to go. Thank you for joining me here today to talk about DataFrames in Java. First, brief introduction. My name is Vlad Zakharov. I have over 25 years of enterprise software development experience, primarily in the Java ecosystem. I also served on the Java Community Process Executive Committee, which is the body that governs evolution of Java platform. And I was a member of the expert group for JSR 335, which delivered Lambda expressions and Stream API for Java, which went live with Java 8. Anyway, so the talk today will talk about DataFrames in Java, but it will also compare and contrast Java implementations with Python and other DataFrame implementations. And we'll specifically be talking about DataFrames in the context of data-oriented programming, which is where it's probably the most fitting tool in your overall data manipulation toolkit. So before we go and talk about DataFrames proper, let's have a brief overview of what we mean by data-oriented programming. And a disclaimer, I'm not going to do justice to this topic, so if this concept is new to you, I recommend looking at these articles at the blogs that you see on the slide. But just to define it, here is a definition given by Brian Getz, who is the architect for Java language. And his definition is as follows: data-oriented programming encourages us to model data as immutable data and keep the code that embodies the business logic of how we act on the data separately. So to understand it better, it probably helps to compare it to another popular paradigm, object-oriented programming. And it's really the difference between those two approaches is in how we treat data or state and behavior, right? So with object-oriented approach, we all know about the need to encapsulate, to protect your privates, to kind of model our system as objects responding to messages, but we also use ideas like polymorphism so that we don't necessarily know which instance of which class at runtime will be responding to message. And that hides not just the data, but also the behavior. The implementation of the behavior is not necessarily known at the time you write your code. With data-oriented approach, you basically do the opposite. You model your domain as pure state, as a collection of properties. So think of it as a collection of Java records or a database table or, I don't know, an Excel table. And, well, maybe not Excel table, but the idea is that you just have pure data and you operate on the data by writing functions that have access to naked data, if you will. And that data is obviously best kept immutable, because if you have multiple functions operating on shared state, then if they can mutate it, bad things will happen. So very different paradigms. One or the other could be better choice depending on the context. Again, we're not going to go too deep into when one works better versus the other, but I do mention some of these kind of decision points on the slide, and I again refer you to the blogs, to the articles, to kind of get more in-depth understanding. But to make it a little bit more concrete, let's look at this distinction between object-oriented and data-oriented approach in a particular domain. And this domain is a donut shop, and this shop sells donuts, ships donut orders to customers. And we'll be using this domain throughout the presentation. So this is kind of the introduction. Our main entities are the donut shop itself, which has customers. Customers have name and address. Then there is a menu of donuts available with their name, price, and discount price if you buy a lot of them. And then you have donut orders. And the way you represent it in object-oriented approach is by modeling each one of these entities as a class, potentially hiding implementation details. And again, you may not even have state on the object. State is just a useful abstraction. But when you ask object for particular state, like how much is this order, it could be a calculated value, it could be directly stored, it could be coming from some helper object. It's all completely hidden. With a data-oriented approach, you just have 3 tables. Again, could be lists of Java records, could be database tables. And then if you want to implement some behavior, you just write, in this case, a Java function operating on a list of donuts. And this function finds top 3 best-selling donuts by quantity. And this is basically Java code, modern Java code that does data-oriented programming in Java. In fact, Java support for data-oriented programming has been evolving, and there are a lot of features added, like some of them you see on the slides. Records, sealed classes, pattern matching, let you manipulate these types of objects directly. And then, of course, collections, streams, and maps let you do set operations on collections of these entities. Having said that, these features do come at a cost. So one is overhead, and you see this is actual overhead computed using Java Object Layout Framework for each one of these records. So this is just simply what it costs you to have one instance of these. And that's really not a lot, but it will add up if you have millions or billions of these objects, which happens in some real production environment. The code readability is fine. It's certainly better than if you had like a bunch of nested loops and for loops and if statements, but it's still not amazing, right? You kind of can't just take one look and immediately understand what's going on there. And also when you define Java records, well, records are still classes. So if your domain is not stable, if you have to do a lot of refactoring, maybe you're like in an early exploratory phase of your development, or maybe you don't even own the data schema, the data structure that you work with, you may have to refactor a lot, and that comes at a cost. And of course, one quote-unquote flexible and powerful way to model pure data in Java is to use maps of maps, potentially of maps, and so please never do it. OK, so now let's throw a data frame into a mix. And data frame is just a data structure. It's a tabular data set, which is made up of columns of different types, again, similar to a relational table. Here is an example of a data frame on the slide. And these are donut orders. And again, looks like nothing special there. Looks like a table. And of course, one question could be like, OK, if this looks like a relational table, why don't I just use a relational database to do operations on these data sets? And well, the answer is, of course, you can, but that requires a database, right? So if you don't have a database in your pipeline, or the database doesn't have the data that you want to operate on, then inserting it just for the sake of doing some filtering, aggregation, transformation may be just too much in terms of the cost, both development cost, infrastructure cost, processing time, and so on. So as I sort of alluded to in the previous slide, data frames give you ability to easily transform data. You can think of it conceptually like relational database operations. You can aggregate, you can join, you can filter. And it does do it in a way, because it operates at a high level, that it makes it easy for developer. We'll see, of course, code examples shortly, but it also makes it easy to separate the data manipulation logic from the data itself, and even externalize that logic and take it out of your applications. Another thing that DataFrames are good at, again, we'll see examples of that, is that they can do a lot of optimization under the covers, right? So they can use efficient collection frameworks, which are much more efficient than your standard JDK collections. They can do things like object pooling to save memory and to improve performance without any effort from sort of developer writing code. And yeah, like I said, could be much more efficient compared to alternatives. So if you already have a database with all the data you need, use it. But if not, this is something to consider. And these are not really specifically talking about Java DataFrames. This framework has been around for some time, and they're used in real-world production scenarios for things like data transformation, data enrichment, reconciliation, and many other use cases. OK, so let's look at some code. And for our first example, we're going to look at the 1 billion row challenge problem. And this is a challenge that Gunnar Morling, you see his, I guess, social media coordinate on the slide, came up with and it ran in January of 2024. And the idea was to see how fast a Java program can process and aggregate a large data set. In this case, 1 billion rows of temperature measurement values. So you have a file with 1 billion rows. It has a weather station, which is just some location somewhere on Earth. And it has temperature measurement. And what you need to do is calculate the minimum, average, and maximum temperature per weather station. And so yeah, there is just one caveat. The file has 1 billion rows. So if you haven't heard of it, I highly recommend checking it out. You can find the challenge and the solutions on the slide. And the reason we're looking at it is not because we have any hope of beating the winners of the challenge, but because it's a basically classic data-oriented programming problem. It makes no sense to design elaborate object-oriented domain for this task. And so we'll see how well DataFrames, different DataFrames can handle it, and also how easy it is to read and, well, to write and to read the code, how concise, how expressive it is. But before we dive into that, just a quick kind of overview of the results of the actual challenge. And those results are pretty amazing. So the top 3 results all finished in about 1.5 seconds. And if you look at the top results, they do have a lot in common. And they're all long, right? It's many hundreds of lines of well-formatted, well-factored code. They do use the APIs that developers don't usually use in their daily coding activities. Things like vector API, other low-level APIs, some experimental JVM features, and because of that, it's not immediately obvious how these algorithms work, and although some of the code is, some of those solutions are pretty well commented. And also, it's not obvious what the code does functionally. Obviously, when you look at it, you know that it solves 1 billion row challenge, because that's what it says. But given this a solution, it would take you some time to figure out what is it that it actually does. And all these top solutions, people worked on them up until the challenge deadline. So it's basically, you can think of it as the time to market for them was about a month, since it ran for a month. And again, it's a fun challenge. It all made sense, and it doesn't mean that there is anything wrong with the code. But in real life scenario, we don't necessarily want to squeeze every CPU cycle out of our solutions. We want to optimize for things like maintainability, developer time, time to market. And so what if we flip our requirements and we focused on achieving those metrics? So let's throw in DataFrame. So we'll look at, for this part, we'll look at 4 DataFrame implementations. First one is Python Pandas, and it's something that I suspect most people think about when they hear the words DataFrame. So this is here just to sort of establish a benchmark, both in terms of performance and in terms of code readability. Again, how easy it is to write, how easy it is to read. We'll look at DataFrame-EC and Tablesaw. They are pure Java DataFrame implementations. And disclaimer, I'm the author and the committer for DataFrame-EC. And well, I picked Tablesaw because it's another implementation, which is pure Java. It seems to be actively maintained, and it's used in various other projects. And the last one we'll look at is Kotlin DataFrame. So Kotlin comes with a DataFrame library. It's not Java, but it runs on JVM, so it's an option that is available to folks working on JVM. And people seem to be intrigued by all things Kotlin, so I decided to throw it in there. The file format is what you see here. So this is what the actual file looks like, except in real challenge, there is 1 billion rows in there, and the code you're going to see will work with 1 billion rows or however many. So we break this into 3 steps: load data, perform aggregation and sorting, and then just print results on the console. So let's start with, and then at the end we'll look at performance and memory usage comparison between all these frameworks. So starting with Python Pandas, the code here is pretty straightforward. Even if you don't know Python, it's kind of easy to figure out what's happening. The read CSV method reads CSV. File is a variable where we have file name, and it has these nice named parameters. So you can kind of look at it, and it will be clear what's happening, and we get our data frame parsed and loaded. Processing. So we want to group by with aggregation. There are 2 options here. One does group by aggregation and then sort. So we want results to be in a consistent order, so we will also have a sorting step. And by default, group by and aggregation do sorting. I read in the documentation that doing sorting separately will result in faster performance. I frankly haven't seen the difference, but these are 2 options, so I'm showing them on the slide. So again, it's pretty straightforward what's happening here. The only thing to call out is after you do aggregation, you end up with hierarchical columns, which is a feature of Pandas. So to print it out, we just flatten the column hierarchy to make it easier to work with. And this is your standard Python iterator pattern, the for loop. So we iterate through the rows and just print the formatted view of each of the rows. And here we are, done. So let's look at the Java examples. So we'll start with DataFrame-EC. We first thing we do, we get file location, then we define the schema. We, unfortunately, I think, although it's a controversial topic. We don't have named parameters in Java, but we use this builder pattern. So again, it's pretty straightforward, I think, to see what's happening here. You have two columns, station and temperature. Your separator is a semicolon, and there is no header line, so you kind of specify all that. And then you create a data set which links that schema to an actual physical file location, and you load it as a data frame. So here it is, parsed and loaded. Aggregation or processing. So again, that looks pretty straightforward. You think of it as doing group by in your kind of relational world. So you aggregate by, and then you have a list of functions, and the aggregation function takes the column you want to aggregate and the name of the target column. So you have these aggregations, then you sort by weather station. Well, you group by weather station, and then the next step you sort by weather station. Now, you may be wondering what this immutable business is, and we'll talk a bit about it in a bit, but just to quickly clarify things, DataFrame-EC is based on an open source library called Eclipse Collections, and Eclipse here as in Eclipse Foundation, not Eclipse IDE, and it's a fully compatible replacement for JDK collections. So it's like for existing kind of data types, you can just do a drop-in replacement, but it offers a lot more collection types, including full support for primitive and immutable collections. And DataFrame-EC is based on that, so thus you see in the name. And immutable here is just a factory method that creates an immutable list, in this case of aggregation functions. Okay, and output just uses a standard for each pattern. We iterate over the rows of the database, and it takes a lambda where we pass in a row object, and then we just print it. So fairly straightforward and fairly similar to what we saw in Python. Tablesaw, surprisingly, or well, maybe unsurprisingly, works exactly the same way. You get the file, you define the schema. One difference here, so the data frame object in Tablesaw is called table. The only difference here is that if you don't have column names, you can't specify them in your schema, so we have to name our columns after we loaded the file. Aggregation and sorting, aggregation, grouping by, and sorting work again the same way. You also don't get to name the columns here, so the column names min and max are created for you, but otherwise it's very similar to what you saw with DataFrame-EC. And the output works pretty much exactly the same, so we're not going to spend any time on this. And so if you look at it, you kind of may be wondering, are those frameworks all the same? Are those APIs all the same? And the answer is sometimes, but there are instances where there are major differences between the code you write based on frameworks, APIs, and some design choices. So we'll see examples of those in a bit. OK, now let's look at Kotlin. So loading bit is pretty standard. Not going to spend much time on that. Processing is interesting. So there are a couple of things I want to call out. First of all, group by actually physically groups by data and creates materialized data frame of data frames. And that has to have some cost memory-wise. And then when you look at the aggregation, you see this weird syntax where it says into. Well, that's actually a Kotlin feature that lets you write internal DSLs like this. So into is not a part of the language grammar. It's an infix function, which I guess in a situation like this may make it easier to read code, but it's obviously coming from Java, seeing infix functions and somewhat unusual. And then sort by works as expected. The iteration, the output using for each pattern, again, pretty straightforward. So we can skip that and look at the performance, specifically execution time and memory usage. So first, you see we talked about 1 billion row challenge. And this is not the 1 billion row challenge. This is a 100 million row challenge. And the reason we had to introduce that was because Kotlin just didn't finish the 1 billion row challenge. And we could talk why it's so, but I wanted to have a comparison in sort of the same context. So we created 100 million row challenge. Yeah, the way to read this slide is the first for each of the frameworks. We have Python, DataFrame-EC, Tablesaw, and Kotlin. The first column is execution time, split between time to load and time to aggregate. And the second column, the purple one, is maximum heap size. Well, with the caveat that for Python Pandas, there is no heap, so it's space used by the operating system process. So I think we have a pretty good idea about Kotlin. Let's look at the 1 billion row challenge results. So a couple of things kind of stand out. In terms of performance as measured by execution time, Python comes pretty much ahead of everyone by some significant, well, relatively significant measure. But it's really not doing great when it comes to memory usage. And that could be, that's likely to be a limiting factor when you run on like commodity size hardware. And that's just a feature of Pandas, right? So if you want something that's memory efficient at like large memory volumes, it's not going to work for you. For the Java frameworks, we have 2 measurements for each. One with 16 gigs of heap allocated, the other one with 32. And the idea was to just compare how frameworks behave under some level of memory garbage collection pressure. So the results, as you can tell, Tablesaw is actually a bit faster when it comes to loading data. And when both frameworks are under pressure, they use all the available memory. But when memory pressure is removed, Tablesaw actually is more memory efficient than DataFrame-EC. But then interesting thing happens when it comes to aggregation. Tablesaw does worse than DataFrame-EC by kind of an order of magnitude. And I'm not exactly sure why. I haven't debugged it. But it does rely, for its aggregation implementation, on Apache Commons libraries. And Apache Commons weren't designed with a lot of attention paid to efficiency and performance and speed. So that could be hurting them. Now, both DataFrame-EC and Tablesaw do much better than Kotlin, well, in general, because they could finish it, but also if you look at performance and loading performance and memory usage, they both rely on highly efficient collection frameworks. So for Tablesaw, it's fastUtil. And for DataFrame-EC, like I mentioned, it's Eclipse collection. So that really shows here. OK. So moving on, I'm just going to spend a couple of minutes talking about DataFrame-EC, what makes it interesting. And the first thing is the grammar for the expression DSL, which is an external DSL, just like strings, we'll see examples, that used for computed columns, filters, and any other kind of data manipulation expression. You can extend the DSL functions and the aggregation functions at runtime without touching the framework. It's also very flexible when it comes to handling nulls, and you can add custom behavior when you want to handle nulls in certain contexts in a special way. Again, this is driven by the needs of like legacy enterprise data flows where nulls could be interpreted in a number of weird and wonderful ways and not what we would like to think null means from the sort of pure computer science perspective. Like I mentioned, built on Eclipse collection framework and benefits from the underlying efficiencies. And it does expose, as you saw, Eclipse collection types in its API. But again, that's kind of a hard dependency, so there is no need to try and hide it. So this is more about Eclipse collections, and it tells you what it kind of adds on top of your standard JDK collections. And I ticked off the features that DataFrame-EC takes advantage of. But to see what DataFrame-EC, and same applies to Tablesaw, how it actually works. If we look again at the data frame that we saw earlier, this is our donut order data frame, and it looks again like a table. If we peel off the cover, we'll see that we actually have a lot happening under the covers. So we use primitive collections, primitive lists. And here you see examples of int and double lists to store primitive values. There is a pool type for pooling objects. So all strings, dates, etc. get pooled, which you actually benefit a lot in kind of real life data sets. So by the way, another example of that is the 1 billion row challenge, where we have 1 billion observations, but in the data sample that was used, there are only 400 odd weather stations, so you get like a lot of compression from using pooling under the covers. And then you have data structures like, for example, bitmap, which is mutable Boolean list, but it's a bitmap under the covers, which used for marking null primitive values, since we don't have primitive for nulls, but we want to support null primitives. And other data structures like multimap used for indexing. For example, if we want to index data frame by name, we'll get that data structure you see on the left, on the right. Okay, so there is a number of, which we're not going to go into, but there is a number of APIs, like fairly rich APIs that go beyond your standard, map or for each, that were again very much inspired by Eclipse collections, which kind of rather than having some small number of very generic APIs, tries to provide reasonable, functional, rich APIs that kind of driven by the real use cases. And now let's look at more functionally interesting scenarios and see how different frameworks operate differently with those. So again, we're sticking with our donut store example. We have 3 entities: customers, the menu of donuts, and the orders, which are all represented as these tables, since we're sticking with the data-oriented paradigm. And in this case, these tables will be data frames in their respective frameworks. So for the purpose of this exercise, we only look at pure Java DataFrames, DataFrame-EC and Tablesaw. But all the code is on GitHub, and there are Kotlin and Python examples as well as like pure Java collection-based examples. So Okay, and we'll look at 4 use cases. List donuts in the popularity order, similar to what we saw at the beginning of the talk. Figuring out priority orders for tomorrow. So just somewhat arbitrary, I decided priority orders are large orders with quantity greater than or equal to 12, or orders that go to customer named Bob. Then we compute total spent by customer, so basically add up the prices of all their orders. And the last one will let us look at the pivot functionality, and that's just a donut count per customer per day. So listing donuts in popularity order, we're actually not going to spend much time on that because it's very similar to aggregation and grouping we saw with the 1 billion row challenge. The only difference here is that we sort by quantity. So we sort by quantity in descending order because we want the most popular donuts first, and then ascending order by donut name just to break ties so that we get consistent ordering even when the quantity is the same. And the last method, because we only care about donut order, not the actual quantities, we call keep columns, which drops the rest of the columns and just keeps 1 column donut. And here is our answer. Doing it with tables, so pretty much the same, slightly different method names and slightly different way of specifying sort order, but otherwise, again, visually, conceptually, it's the same. And again, when you think about solving a problem with DataFrame, helps to think about how would I do it with relational world, right? How would I do it with SQL? And so, you would do group by, et cetera, and that's how it works. Now, this is where we see some differences. So priority orders for tomorrow. With DataFrame-EC, we have a method on the DataFrame called select by, and it takes an expression that basically gets translated into like internal expression and gets executed, applied to the data frame. Tomorrow is just simply a local date variable containing whatever tomorrow is. So this is this internal DSL. It's like its own language, but I would argue that pretty much all of you should be able to look at it and figure out what's happening here. You don't need to like read the manual or learn things, go up some steep learning curve to see what this means. And it should be equally easy to figure out how to write expressions like this. Another thing, another benefit of this is you can take it out of your Java code, you can put it in a configuration file, you can put it somewhere, externalize it. And the reason you would want to do it is because, well, this is a piece of business logic, and maybe you want your business users, depending on your context, to actually own the business logic. And this is something that, again, can live outside your software, and then the accounting department or the operations users or whoever can actually work with that. If we see how it works with internal DSL, right, where it's just Java, and this is a Tablesaw example, again, it's very similar. You have a where method, but the expression itself is a Java expression. And I guess the benefit is if you type something wrong, your IDE will tell you with a red squiggly, but you still have strings here, so you still need, well, you need to test your code for many reasons. But another problem with this is that it's, well, you can look at it, it's pretty nice declarative code, but it's still probably harder to parse for a reader than the previous example. And it's pretty much impossible to externalize. So if you say, OK, we want business to own the logic of what priority order means to us, and we want to govern it separately from the application code, well, you can't do it, right? You can't, or you can't give your donut shop whatever employee access to Java ID and have them submit pull requests every time they want to change this definition. Okay, total spend per customer. So how do we calculate that? Well, we need to calculate the dollar amount of each order. To know that, we need to know the quantity and the price. And the price we use depends on the quantity. So we want to bring together the donuts with their regular price and discount price and join it to the order data set. And then we do our usual group by and aggregation and sort by customer. So joining works very straightforward with the data frames. You specify, and so I'm just showing both on the same slide because, again, they are so similar. And simple, you specify which column you want to join by. In case of DataFrame-EC, the first example, you can also specify which columns you want to bring from the data frame you're joining to. And in this case, both will produce the same result, which is a data frame which has 2 columns added to it. The next one is another example where you have difference between external DSL for expressions that you see here and internal DSL we'll see on the later slide. So this is exactly the formula that you saw when we looked at the requirements for this use case. Quantity less of 12, use price, otherwise use discount price and multiply by quantity. Again, it's, I would argue it's very, very readable. You don't need to specify the column type because under the covers, everything is actually strongly typed and there is type inference being done for you. And if you get, if you try to, I don't know, multiply quantity by donut name, you will get a meaningful error message telling you that you, well, shouldn't be doing that. With Tablesaw, again, here's an example of what normally would be like nice declarative code. You do need to specify. You do need to specify column type, but then again, you can read it. You can figure it out. If quantity is less than 12, use this. Otherwise, use that. But it's a lot of text to express this simple piece of logic. And again, it's baked into your application. It's not externalizable. In Tablesaw, there is also a way to do it like this in a sort of imperative fashion rather than declarative. But declarative approach is probably better in this context. Okay, and aggregation and sorting, that pretty standard. We saw that before, so not going to spend time on it. Donut count per customer per day, that just shows that it's very straightforward to implement pivot, similar to like pivot functionality you would have in Excel with data frames. And again, side-by-side examples, because they sort of work the same way. 2 differences to call out. In DataFrame-EC, you see the parameters to pivot by and to the values to aggregate as lists because it supports multiple dimensions and multiple aggregation values, just like Excel does. In Tablesaw, you can only have 1 of each, but for this example, they both work. And if you don't have values to aggregate for particular coordinates in your pivot table, Tablesaw will just say it's a missing value, which is, I guess, it's equivalent of null. DataFrame-EC will actually have the value as 0. Again, we can have a philosophical discussion which one is more correct. But you can change this behavior if you feel it should be done differently. All right, so some takeaways. Java DataFrame, useful addition to your data manipulation toolkit. again, when you have a use case that seems like a fit for data-oriented programming paradigm, before you get your data in a list of records or in a relational table or a Spark cluster, see maybe a DataFrame solution would be a better approach. It's especially compared to things like Spark cluster or maybe even actual relational database. You can actually process a lot of data relatively quickly on commodity hardware. So something to keep in mind. Common scenarios, ad hoc manipulation, playing with the data. So things you may do using, let's say, Python, Pandas notebook. And this is what people tend to reach for when they have this this need. But then you end up with a piece of code that solves your problem, but it solves it in Python, and your backend is a Java service, and now you have to figure out how to rewrite it. If you use a Java DataFrame, you could just simply take this code and basically stick it in your program. And then you can use it to programmatically transform query analyze data, so your standard enterprise data processing pipelines can benefit from it. And of course, your kind of standard use cases for DataFrames for data science notebooks and visualization are supported by some of the Java DataFrame frameworks. And this is the last slide. So this talk is available on GitHub with the sources. I think the slides will also be available at the conference site. You have links to DataFrame-EC and Eclipse collections, and a couple of other pure Java DataFrame libraries to check out. So when it comes to Java DataFrames, you have choices. So go explore them and have fun with DataFrames. Thank you. And do we have time for questions? Yes, we do.
Thank you. Two practical questions about DataFrames, and I think I may already know the answer, but I'm going to check anyway. First of all, one of the major points about databases, obviously, is you have constant change. Tons of inserts, tons of reading, mutability, et cetera, et cetera. I'm assuming that you're not really concerned about with DataFrames. You have a static data set, you read it in, you analyze it, right. You're done. Is that correct? Yeah.
So one scenario is, and again, just looking at the real sort of life enterprise data pipelines, which may not necessarily be scenarios you have to deal with, but a lot of data is just files, messages. They're detached from their store of record, which may be a database, and whether we're talking about various business units within a company or different companies, financial institutions exchanging data, a lot of it, if not most of it, is files. And so when you build the data processing pipeline, okay, maybe the final resting place for your data needs to be a database for whatever reasons, but for data enrichment, data transformation, data validation, you just have a file which is this static piece of data and also nice recovery point, and you just kind of work with it with your data frame. Okay, any more questions? Nope. Right. Well, thank you very much.